In this video, we will dive into data warehouses, one of the most powerful concepts in modern business analytics. Data warehouses are much more than storage. They are the beating heart of business intelligence. Today's organizations are swimming in data from everywhere. The challenge isn't about getting data anymore. It's making sense of data. So let's get started. Previously in this class, we discussed the fundamental distinctions between operational system and reconcile system. Imagine we run a restaurant. Your operational systems are like the kitchen during dinner rush, taking orders, cooking meals, serving customers. Everything happens in real time. You need speed and accuracy, handling one transaction at a time efficiently. And that's Salesforce, your ERP system, your POS terminals. These are engines running our day-to-day business. But at the end of the month, maybe we ask, what dishes are most popular? Which servers sell the most desserts? How do weekend sales compare to weekdays across different locations? So suddenly, we're analyzing patterns across thousands of orders, multiple systems, over time. That's where reconciled system or data warehouses come in. They pull data from operational silos, clean the data, integrate it, and present it so we can see the big picture. So different jobs need different tools. In today's class, we are going to first talk about the fundamentals of data warehouse. Then we will talk about dimensional modeling, and we will learn how we can build dimensional models. In the last video, we talked about data integration, and we understand that data integration is a constant need because departments implement separate systems for their specific goals. So the challenge here is how do we pull data together from different siloed systems to form a unified view? There are two different ways that define how we use data: online transaction processing and online analytical processing. OLTP, which stands for online transaction processing, is this do something right now system. When you click buy on Amazon or when a bank processes your withdrawal, that's OLTP. So the characteristics are we try to insert, update, delete operations constantly and process small bits of data at a time. Here, the speed is everything and highly normalized to avoid data redundancy. And we always focus on current state. OLAP, which stands for Online Analytical Processing, is completely different. This system is, let me think about patterns processing, analyzing how have our top 10 products performed across all regions in the last 3 years. So here we have read-only queries mostly, and we have complex aggregation analysis across different dimensions, have large volumes of historical data, and oftentimes we work with denormalized structures and cross-system integration. So think of OLTP as a busy emergency room, handle each patient quickly, and OLAP is medical research, examining thousands of patient records over years to find patterns. Both of them are critical, but require fundamentally different database design. So now let's talk about OLTP in more detail. And let's picture a busy coffee shop point of sale system. Each transaction is a small, fast, precise transaction. The database here is highly normalized. You have one customer table, one product table, one order table, all linked very efficiently. But OLTP doesn't handle show me coffee sales trends by neighborhood correlated with weather patterns over the last 2 years. That query would join multiple tables, scan millions of rows, and potentially lock up your system while people are waiting for their morning coffee. So OLTP maintains current state beautifully, but historical data often get overwritten. And over time, organizations recognize that operational system optimized for OLTP cannot handle analytical tasks very efficiently. And this is because the OLTP system focuses on current data, but does not focus on historical data. And also, it cannot handle complex queries. And oftentimes, we have data quality issues. We have missing data and missing context. So now we need OLAP. OLAP is designed for complex questions, and these require historical depth. So when executives ask, how did Q3 sales compare to last year across all product lines and regions? They need data integrated from multiple sources, spanning months or years. So the key OLAP features are heavily read. So we are querying, we don't update. And we have large result sets aggregating millions of transactions. And there is a historical focus, and we are trying to compare trends over time. And also, data is often denormalized, trading storage for query speed. So think of this as stepping back to see the forest, not just individual trees. OLAP let us spot the patterns invisible in day-to-day operations. Again, as we discussed before, we need different tools for different tasks. OLTP is optimized for transactions and is great for day-to-day business, but OLAP is the analytical engine. Previously in this class, we also talked about different approaches to data integration. And more specifically, we have data consolidation, and we have data federation, and we also have data propagation. And data warehouse focus on the first one. So data warehousing focus on the first one, data consolidation. Here we extract data from multiple sources, we transform it, we load it into a central warehouse. These create a single source of truth, and this is the most structured approach and allow us to do comprehensive historical analysis. What is a data warehouse? A data warehouse is a dedicated data store that takes information from internal and external sources, quality controls it, and then consolidates it into a unified, consistent view to support decision-making across the organization. The key benefits are substantial. It provides centralized data services, achieving a true single source of truth. Data quality is improved through necessary validation and cleansing, and because it is separated from operational system, it eliminates resource contention, allowing those operational systems to focus on their primary purpose. If the data warehouse has enterprise-wide scope, managing very large historical data for strategic decisions, a data mart is a data warehouse in a smaller scale. So data mart has a department-specific focus, containing a smaller subset of data, often sourced from the data warehouse, and serve as a target group for tactical decisions. Organizations often use a combination of both data warehouse and data marts to meet a wide range of analytical needs. So data in a data warehouse has 4 unique defining characteristics. First is integrated. It hosts a single source of truth, systematically consolidating data from multiple systems. The second is non-updatable. Data is loaded via planned batches, but end user cannot directly update or modify it. The third is time variant. So data explicitly contain a time dimension, allowing you to study trends, changes, and historical events over a long period of time. The last one is subject-oriented. The data is organized around the key business subjects, like sales, marketing, or finance, rather than focus purely on transactional processes. In a typical data warehouse architecture, data starts in the internal and external source systems, and then it's extracted and placed in the staging area, where it's scrubbed, cleaned, enhanced, and combined. Then it is loaded into the data warehouses. The subsets often refresh downstream data marts. Finally, the end users access the data using various reporting and query tools. So I have a side-by-side comparison of operational systems versus informational systems, and data warehouse is informational systems. So operational systems exist to execute daily operations using current transactional data with the goal of fast transactions. On the other side, Data warehouses exist to support analysis and decision-making using historical integrated data with the goal of query performance. Now let's move to dimensional modeling. The data model behind the data warehouse is called dimensional model, which is a specialized, simplified relational model that supports OLAP. The traditional relational model, OLTP, is heavily normalized, resulting in complex relationships. The dimensional model, OLAP, simplifies everything into two primary entity types, facts and dimensions. So facts here are the measurements, and dimensions are the descriptive context. It uses a simplified star-shaped structure, also called a star schema, and it is intentionally denormalized for lightning-fast analytical query performance. Now let's define the players. First one, measures or facts. These are the numeric metrics that present your data objectives. These are the numbers you actually want to analyze, like the quantity sold, revenue, profit. These are quantitative and the focus of the analysis. On the other side, dimensions or descriptors are the descriptive entities that provide the essential context, the who, what, where, and when of your measures. The examples will include time periods, customers, or regions. They enable slicing, dicing, and comparison. So remember, 50,000 units sold is meaningless without the dimensions to provide the context. Business questions naturally frame themselves using these concepts. When a stakeholder asks, show me the average profit margin for a premium product. So here the profit margin is a measure and the premium product is a dimension. So once we receive a question like this, you can immediately identify the necessary facts and the context needed for the model. Dimension models directly support business questions. So for example, what were total sales by region last quarter? So here the measure is total sales. The dimensions are region and time. Or second question is how many premium customers purchased electronics in December? Here the measure is the count of customers, and the dimension here is customer segment, that's a premium customer, product category, electronics, and the time is December. So notice here the pattern. The business questions really express the measures quantified by dimensions. And the dimensional model are designed to answer those questions very efficiently. Dimensions often contain natural hierarchies supporting different levels of analysis. For time, we can start with annual sales and we could drill down to quarter, then monthly, then daily, or we can roll up from daily to monthly to see the big picture. And geographically, we can have country, region, state, and city. So hierarchies are like zoom lenses. Start with a big picture, and then you can zoom in as needed, or you can start with details and zoom out for context. I also would like to introduce a concept, data cube. And the data cube helps us visualize dimensional models. And this is a multi-dimensional space where each edge represents a dimension. So imagine we have a three-dimensional cube. The X here is location. Here we have Chicago, New York, Toronto, Vancouver. And we have Y-axis, which are the time from 2022 to 2025. And we have Z-axis. Here we have different products, shirts, ties, pants, and shoes. Each cell in this cube contains a measure, let's say a sale amount. So the intersection of Chicago plus 2024 plus shirt give you $350 in sales. So now you can slice the data, dice the data, drill down, or roll up. So while we can only visualize three-dimensional spatially, the concept extends to models with many more dimensions. So sometimes people call this as hypercubes. The principles remain the same. The measures are qualified by different dimensions and they are ready to be explored. For data cube, we have two very commonly used operations, slicing and dicing. Slicing means filtering through one dimension to create a slice. For example, we can show me all the products and cities for year 2024. So you are fixing the time dimension at a year 2024, creating a two-dimensional table of location times product. All the data is there, but you are looking at one time slice. Dicing here is to create a small cube, a subcube. We are filtered by multiple dimensions to get a smaller cube. So for example, we can ask, show me the shirts and ties sold in Chicago and New York during 2023 and 2024. Now you have a smaller cube with only two products, shirts and ties, two locations, Chicago and New York, and 2 years, 23 and 24. So these two operations, slicing and dicing, allow us to focus analysis exactly where you need it. If you want to compare product performance across regions for a specific time period, you can slice by time, dice by region and product. In addition to slicing and dicing, there are two more critical operations in DataCube, and they are drilling down and rolling up. We perform drill down by moving from a summary view to a detailed view, navigating down the hierarchy, for example, from annual sales to quarterly sales and then to monthly sales. Rolling up is the reverse. We try to aggregate data from a detailed view to a higher summarized level. For example, moving from monthly to quarterly and to annual sale data. So think of drill down as zooming in with a microscope and roll up as zooming out to see the landscape. Both are essential for understanding data at the right level of detail for decision making. The Star Schema is the specialized architecture that makes OLAP work. At the center is a single fact table. This holds measures and foreign keys. Surrounding the fact table, we have many dimension tables, and they hold descriptive attributes. The relationship is strictly one-to-many between each dimension table and the center factor table. Also, there are no interdimension relationships. This will maintain a clean star structure. In this HR star structure, you can see the central fact table is employee satisfaction. These include measured satisfaction scores and turnover rates. And here we have some surrounding dimension tables: time, employee, department, location. These dimension tables connect to the center fact table. And this star structure immediately enable analysis across those different dimensions. So for example, we can ask questions such as, which department has the highest turnover rate last quarter? Or how has employee satisfaction trended over the past 3 years by location? Dimension tables hold descriptive values, and they define the business context, and they use clear and textual terminology. They're typically much smaller and more stable than the big fact table we have in the middle. So what goes inside dimension tables? So these dimension tables store descriptive values such as city names, product names, employee names, department labels, so on and so forth. They also focus on discrete values, and they do not store continuous numbers. They have distinct categories such as days of the week or the quarters or specific product SKU numbers. And in dimension tables, we use business terminology that are very familiar to end users. Also, the primary keys as surrogate keys, which we will discuss next. So what is a surrogate key? A surrogate key is an artificial, auto-generated identifier that serves as a primary key in a dimension table, and they are independent of business keys from the source systems. In my example here, I have two source systems, A and B. You can see that in source system A, we use a numeric ID as a primary key, but in source system B, we use alphanumeric codes as primary key. And the data warehouse generate a uniform integer key value, which is customer code, and this is used as the primary key. And this is what we call a surrogate key. So in addition to the surrogate key, we also keep the original keys, which we call this as source PK. And these are kept here for reference. So you may ask, why do we need surrogate keys? Surrogate keys are important because they help ensure uniformity and insulation from source system chaos. Operational systems may change their primary key structure, and this could break everything downstream if you rely on those primary keys. So surrogate keys keep control of the primary keys within the data warehouse. In addition, the small integer values are much faster than multi-column business keys when we perform joins across fact tables. So think of this analogy. The surrogate key here is internal tracking number for a container ship. The containers may have inconsistent external keys from different exporting countries, and these are the source systems. But then the shipping company give it one internal and stable tracking number, which we are using as the surrogate key. And this will help us to make sure that these can be instantly located in a massive central manifest, which is a fact table. When dimension table contain hierarchies, we intentionally denormalize them. Look at the geography dimension. United States is repeated for every state. This redundancy is accepted because this means that our analytical queries will not need slow joins across multiple tables. In dimension modeling, query performance is always more important than storage efficiency. Moving to fact table, this is really the heart of the dimensional model. The fact table is the largest table and continuously growing with new transactions. Its primary key is a composite key, often formed by combining the surrogate keys from all the associated dimension tables. The most crucial concept here is data granularity, or we call this as grain. The grain is a level of detail. The grain must be consistent across all the rows. So if one row records sales for a day, every row must be the daily data. If you mix the grains, your report will be mathematically incorrect. Or as we like to say, never mix grains. In my example here, you can see the trip taken is the fact table. And surrounding this fact table, we have 4 dimension tables. And the primary key here of the fact table is a composite key, which includes all the surrogate keys of all the dimension tables. And the relationship between the fact table and a dimension table is always one-to-many. So choosing the right grain is important. And this often is the hardest design choice. A finer grain, which includes transaction level detail, offers maximum analytical flexibility. You can aggregate up to any level and support future unpredicted questions. The disadvantage here is much larger storage and also much longer processing times. A core-studied grain, for example, monthly aggregated data, is smaller and much faster, but the disadvantage is that you're going to lose the detail that cannot be recovered, and this will limit your future flexibility. The best business practice here is that when you are not sure, you go finer. Storage is becoming cheaper and cheaper, but analytical flexibility is invaluable. You can always aggregate up, but you can never drill down past your defined grain. So analogy here is when you choose a grain, it's like deciding the resolution of a digital map. Do you want the street level details, which will be the fine grain? It will be massive, but you can see everything. Or do you want only the state boundaries, which will be the coarse grain? It will be very small, but if someone later asks for direction to a specific building, that detail is permanently lost. In fact table, we often look at the additive property of measures. And we categorize the measures according to their additive property. And these can be additive measures, semi-additive measures, or non-additive measures. Additive measures can be measured across all dimensions, and these include sales revenues, quantity sold, cost amount, so on and so forth. Semi-additive measures can be summed across some dimensions, but not usually the time dimension. So for example, inventory levels or account balances. In non-additive measures, these cannot be summarized, and these include averages or ratios like profit margin percentage. They must be calculated on the fly. So we talked about what can go into fact table. Now let's talk about what should not go in fact table. So to maintain the purity and the performance of fact table, only measures and foreign keys should be included. You should avoid flags and indicators. So for example, status flags like triple cancelled or is active. These are descriptive attributes that serve as filters, not measures, and they belong in dimension table. The second categories are dates and timestamps. Don't store raw date column. Instead, you use a foreign key to link to a dedicated time dimension. The third is descriptive text. Product descriptions or addresses, those should not go into fact table. And this will significantly increase the size of fact table, and they will create unnecessary redundancy. Now we've covered the dimensional model. Let's now shift to the practical stage. Let's try to learn how we can gather requirements and build data models. Building a data warehouse follows a systematic process. We start with business requirement gathering, and then we build the Fact-Qualifier Matrix to map the needs. Then we will conduct source system analysis, the reality check. Next is dimension model design, followed by ETL development, and finally testing and deployment. So to talk about the process, I would like to use a case study. Let's apply this to a particular case study at IU. This is IU's travel management service. And at IU, they process roughly $30 million every year in travel reimbursement, and this covers over 50,000 trips. Their goals are to minimize expense, ensure compliance, and manage timely reimbursement. The key complexity here is organizational hierarchy. Campuses contain financial responsibility centers, and which will hold the final approval rights. So the fundamental principle here is that the business questions, for example, we need to ask questions like how many international trips per year and account? What is the preferred airline by year? What are the trip types, in-state, out-of-state, international over time? These are not random questions. These are what travel management service need to answer to do their job effectively. You cannot design good dimensional models by looking at a source system. Source systems are designed for transactions, not analysis. Instead, we need to always start with questions. What does the business need to know? What decisions are they making? What trends do they need to spot? We must distinguish between the types of requirements we receive. Here we have operational questions versus analytical questions. Operational questions are specific, transactional, and support day-to-day activities. What is the daily allowance? Or who is a travel ranger? And these are policy questions. Analytical questions, on the other side, are broad, strategic, and support planning. In Data Warehouse, we focus on answering analytical questions that require historical data, cross-functional integration, and trend analysis. To gather requirements, we use multiple techniques. So we can have stakeholder interviews, and these are vital for one-on-one understanding. There can also be collaborative workshops that facilitate group brainstorming and build consensus. We might also use surveys for large population or process observation to uncover workflow inefficiencies. Going back to the travel service, the requirements naturally fall into 4 different categories: trip volume, expenditure, vendor, and process efficiency. It's crucial to also review the different stages in the business process, from travel preparation to execution to reimbursement processing and to analysis and reporting. A complete dimensional model must support analytical across all the process stages, ensuring we capture measurements for everything from request volumes to payment accuracy. Now let's talk about Fact-Qualifier Matrix. The Fact-Qualifier Matrix is a systematic tool that can convert business questions into concrete data requirements. This involves a step-by-step construction process. First, we need to extract the facts, and this requires to identify numeric measures of business interest. For example, how many trips or how much money was spent. Next, we need to extract qualifiers to identify descriptive elements that provide the necessary business context. The third step is to create a matrix. Now the facts will become column headers, and the qualifiers will become the row headers. The next step is that we map the questions, so we place a question number in the cell where fact and qualifier intersect. The last step is to analyze the coverage. We identify the most important facts and qualifiers based on the density of the cell. In the travel service, the measures are the number of trips and the quantities. And when we look for qualifiers, we look for descriptive attributes. For example, these include who, what, where, when, those elements. So in the travel service Fact-Qualifier Matrix, facts are the columns here. So we have number of trips, we have trip expenditure, we have the time to submit reimbursement, and then also processing time. And the qualifiers here are the rows. So here we have the types of different travelers, the account of the traveler, the type of the trip, the destination, the expense category, the airline, hotel, campus, and also the month and the year. So for example, if we have question number 1, which asks, what is the number of trips for each traveler type per month, per year? This is question number 1, so we enter 1 in the intersection of number of trips with traveler types and month and year. So coming back to the matrix, that's why we have 1 put in the intersection of number of trips with travel type, month, and year. Question 2 asks, what is the number of trips per trip type by responsibility center by campus per year? So here, the measurement or the fact is still the number of trips, but the dimensions are different. Now we are looking for trip type, so that's why we put a 2 in the intersection of the fact, which is number of trips, and the trip type. And similarly, we will put number 2 in the intersection of the fact and responsibility center, and also for campus and year. And certainly, you can have many other additional questions. For illustration purpose, I will just use 2 questions here. So this is our Fact-Qualifier Matrix. Now we finished the requirement gathering. Now we can tackle the building data models. Building a dimensional model requires 2 simultaneous analyses, a top-down analysis and a bottom-up analysis. So the top-down analysis is business-driven. The method is FQ matrix, and this shows what users ideally want to analyze. The bottom-up analysis is a reality check. We survey existing data to assess its quality and also the feasibility. The final model often emerges from intersection of those 2 different analyses. If the business requests a fact, but the data is unavailable or unusable based on the bottom-up check, that requirement must be removed or deferred. An important step is now we group the related facts into meters, which become the basis of our fact table. A meter here is a set of related facts measuring the same business context or outcome, and all share the same grain in the business process. For the employee satisfaction meter, we can have job turnover rate, average length of employment, number of employee complaints. The common theme here is they all measure employee happiness or retention. The related meter here will be employee satisfaction, 3 measurements: turnover, employment length, complaint count. For the travel service example, here the number of trips and trip expenditure, they measure completed travel events. So we could potentially group these two, number of trips and trip expenditure, into something we call trip taken meter. So facts about processing time, such as time to submit reimbursement, are about administrative workflow, and they form a separate meter, reimbursement processing. And it rarely makes business sense to create multiple context fact table if they measure the same outcome. Now we formalize the dimensions from our qualifiers. First, so here we're going to eliminate qualifiers where the source data does not exist or is not available based on the bottom-up analysis. Next, we need to remove the false qualifiers. We eliminate attributes of other dimensions that cannot exist independently. The third step is to identify the hierarchies, like the financial structure and the time hierarchy. And now we can build the dimensional hierarchy model. Coming back to the IU travel service example. So in this example, we can see travel account, responsibility center, and a campus. This can become a hierarchy. So within a campus, we can have different responsibility center. Then within each responsibility center, we can have different travel accounts. These are the financial structure. Another hierarchy we can build is the time hierarchy. So we can have year to month. And we also have some single level dimensions, and these include the type of the traveler and also the type of the trip. Now let's move on to create the initial dimensional model. We first place the meter, which is a fact table, in the center, and we will connect all the dimensions to it. And now we need to determine the grain. The minimum grain must be at least as fine as a combination of the lowest hierarchy level across all the dimensions. For trip taken, the minimum required grain is per month, per traveler type, per trip type, per account. However, we can consider going finer. Would daily data or individual traveler data provide flexibility that justify the increased storage and processing cost? And that is the trade-off decision. So to illustrate the process, we first will put the trip taken in the center because this is our fact table. And now we will connect it to different dimensions. So the time is a hierarchy dimension, which include year and month, and we will always connect to the lowest hierarchy. In the time example, we connect to the months instead of connect to the year. And similarly, we will connect to the organizational structure hierarchy. Remember that we said campus will have multiple responsibility centers, and each center will have multiple traveler account. So we connect the trip taken to the organizational structure using a one-to-many relationship. We also connect to the traveler type and trip type, and these are the individual level dimension tables. So this is our initial dimension model. So then we will finalize a star schema by flattening the hierarchies. We can replace multi-table hierarchies like the financial structure with a single denormalized dimension table to eliminate joins. We also need to add surrogate keys. Remember that we created those auto-incrementing integer primary keys in the fact table. We also need to connect to all the fact tables. We also need to connect it to the fact table. We need to add all the dimension surrogate keys to the fact table. And these will form a composite primary key. And then we need to validate the fact table. And this is the most important step. This will ensure the fact table is pure. It must only contain numeric measures and foreign keys. And we need to ruthlessly remove all descriptive attributes. We also need to remove raw date columns. So come back to the trip example. So here we need to think about the count of the trips and also the expenditure of the trips. For multi-level dimensions, we often will have to denormalize them. The denormalization will happen by flattening the hierarchical levels. So in this example, instead of using 3 different tables, I'm actually going to use one single table. In this table, we will have campus, we have responsibility center, we have a traveler account. As you can imagine, because each campus have many different responsibility center and each center have many travel accounts, so I'm going to have a lot of data duplications in this table. But this is totally acceptable. And similarly, we're going to flatten the time structure and create a dimension table with both year and month. The next step is to add the surrogate keys to the dimensions. Here we add the ledger code, travel type code, and these are the surrogate keys, and they are auto-incremental integers. Then we will add the combination of all these surrogate keys into the fact table, and these together form a composite primary key of the fact table. They are foreign keys, and they're connected to each of the dimension table. In the meantime, they're also part of the composite primary key for the fact table. The last step is that we need to validate the fact table. The columns are only the measures or the dimension surrogate keys. We should not have any status indicators or flags. We also should not have any date or timestamps. So fact table should only contain numeric measures that can be aggregated and surrogate keys that link to the dimensions. So that concludes our data warehousing journey. The 4 key takeaways that define data warehousing is, first of all, data warehouse solves integration problem. They provide a reconciled system separate from operations, and this will create a single source of truth. Second, dimensional model will enable analysis. The Star Schema simplifies querying and enables seamless operations like slicing and dicing and drilling down and rolling up. And the surrogate key that we use in the dimensional model provide control for us. These are auto-generated keys that can insulate our data warehouse from chaotic source system changes. And also, the grain determines flexibility. Your finer grain will give you maximum analytical flexibility. When you are not certain, always choose a more detailed grain. We also talked about the systematic process. This includes requirement gathering, FQ matrix construction, bottom-up validation, and Star Schema design. So master all of these and you master the strategical data management. This concludes the video. Thank you for watching.